Today we're diving into the fascinating world of physical quantities, which are essential building blocks in physics and mathematics. Every measurement we make, whether it's distance, time, or speed, falls under the umbrella of physical quantities. But did you know that these quantities can be classified in two main types? That's right, scalar and vector quantities. Understanding the distinction between these two is crucial for solving problems and making sense of the physical world. In this video, we'll explore what makes scalars and vectors unique, how they're used, and why this difference matters in real-life scenarios. Let's get started by defining what a physical quantity actually is. Physical quantity is any property of a material or system that can be measured and expressed with a number. Think of things like length, mass, temperature, or time. These are all physical quantities because we can assign them a value in a unit. For example, the length of a table might be 2 meters, or the temperature outside could be 25 degrees Celsius. Physical quantities help us describe the world in a precise and standardized way, making communication and calculations much easier. Now that we know what a physical quantity is, let's see how they are categorized into scalars and vectors. Start with scalar quantities. A scalar quantity is one that is fully described by just a magnitude or size. It doesn't have any direction associated with it. For instance, if you say the temperature is 30 degrees Celsius, you're giving a scalar quantity. There's no direction involved, just a value. Other common examples include mass, speed, energy, and time. Scalars are simple and straightforward, making them easy to work with in calculation. Next, we'll see how vectors add another layer of complexity by including direction. Better understand scalars, let's look at some everyday examples. When you check your weight on a scale, the number you see, say 70 kilograms, is a scalar quantity. It tells you how much mass you have, but not in which direction. Similarly, when you look at the time on a clock, like 3 hours, it's just a value with no direction. Even the distance you travel, such as 10 kilometers, is a scalar if you're only interested in the total length covered, not the path or direction. These examples show how scalars are everywhere in our daily lives. Now let's move on to vector quantities. Unlike scalars, vectors require both a magnitude and a direction to be fully described. For example, if you say a car is moving at 60 kilometers per hour to the north, you're giving a vector quantity. The speed alone is a scalar, but once you add the direction, it becomes velocity, a vector. Vectors are crucial in physics because many phenomena like force and acceleration depend on both how much and in which direction. Let's look at some common vector quantities. Velocity, for instance, tells you not just how fast something is moving, but also in which direction. If a runner is sprinting east at 8 meters per second, that's a vector. Force is another example. When you push a box, the force you apply is both a strength and a direction. Acceleration, displacement, and momentum are also vectors. These quantities are essential in understanding motion engineering and many scientific applications. Main difference between scalar and vector quantities lies in direction. Scalars have only magnitude, while vectors have both magnitude and direction. This distinction is fundamental in physics and engineering, as it determines how quantities combine and interact. For example, you can simply add scalars together, but adding vectors requires considering their directions. Understanding this difference helps you solve problems more accurately and interpret results correctly. Scalars are often represented by simple numbers or lengths on a line. For example, if you measure a distance of 5 meters, you can show it as a point on a number line. There's no need to specify a direction, just the amount. This simplicity makes scalars easy to visualize and work with, especially in basic calculations or when direction isn't important. Vectors are usually represented by arrows. The length of the arrow shows the magnitude, and the direction of the arrow shows the direction of the quantity. For example, if you walk 4 meters north, you can draw an arrow pointing north with a length proportional to 4 meters. This visual representation helps us understand how vectors combine and interact in space. Adding scalar quantities is straightforward. You simply add their magnitudes together. For example, if you have 2 liters of water and add 3 more liters, you end up with 5 liters. There's no need to worry about direction or orientation. This makes calculations with scalars quick and easy, especially in everyday situations. Adding vectors is a bit more complex because you have to consider both magnitude and direction. For example, if you walk 3 meters east and then 4 meters north, your total displacement isn't just 7 meters. Instead, you use the Pythagorean theorem to find the resultant vector. This method ensures you accurately represent both the size and direction of the combined movement. Multiplying scalars is just as simple as adding them. If you have a mass of 5 kilograms and multiply it by 2, you get 10 kilograms. The result is still a scalar and there's no direction involved. This property makes scalars very convenient for basic arithmetic operations in science and daily life. When you multiply a vector by a scalar, you change the magnitude of the vector but not its direction. For example, if you double the force applied in a certain direction, the force vector becomes twice as long but still points the same way. This operation is common in physics, especially when scaling forces or velocities. Dividing scalars is just as straightforward as multiplying or adding them. For example, if you have 100 meters and divide it by 4, you get 25 meters. The result is still a scalar and there's no direction to consider. This simplicity is one of the reasons why scalars are so widely used in basic calculations. Dividing a vector by a scalar reduces its magnitude but keeps its direction the same. For example, if you have a velocity vector, the speed becomes half as much but the direction remains unchanged. This operation is useful when you need to scale down a force or velocity in physics problems. Scalar product, also known as the dot product, is an operation that takes two vectors and returns a scalar. For example, if you multiply two vectors and the result is a number, not a vector, you've performed a dot product. This is commonly used in physics to calculate work done, where force and displacement are multiplied to get a scalar value. Vector product or cross product is another way to combine two vectors. Unlike the dot product, the result is a new vector that is perpendicular to both original vectors. This operation is important in physics, especially when dealing with rotational motion and torque. The cross product helps us understand how forces interact in three-dimensional space. Scalar quantities are always measured with units such as meters for distance, kilograms for mass, or seconds for time. These units help standardize measurements and make it easier to communicate results. Using the correct units is essential for clarity and accuracy in science and engineering. Vector quantities also have units, but these units reflect both magnitude and direction. For example, velocity is measured in meters per second and force is measured in newtons. The units help specify not just how much, but also in what direction the quantity acts. This is crucial for solving problems involving motion and forces. Scalars are typically represented by regular letters or symbols, such as m for mass or t for time. There's no need for arrows or boldface type since direction isn't involved. This simple notation makes it easy to distinguish scalars from vectors in equations and formulas. Vectors are usually denoted with arrows above the letter or in boldface type. For example, velocity might be written as v with an arrow, or as a bold V. This notation clearly indicates that the quantity has both magnitude and direction, helping to avoid confusion in calculations. Scalars represent quantities that don't depend on direction. They answer questions like how much or how many. For example, the energy stored in a battery or the amount of time it takes to complete a task are both scalars. These quantities are essential for measuring and comparing different aspects of the physical world. Vectors represent quantities that depend on both magnitude and direction. They answer questions like how much and which way. For example, the force you apply to push a door or the velocity of a moving car are vectors. These quantities are vital for understanding motion, forces, and interactions in the physical world. Distinction between scalars and vectors is more than just academic. It affects how we solve problems, interpret results, and design experiments. For example, when calculating the total distance traveled, you use scalars, but if you want to know the shortest path from start to finish, you need vectors. This difference is crucial in fields like engineering, navigation, and physics. Scalars are everywhere in our daily lives. When you check the temperature, measure your height, or read the time, you're dealing with scalar quantities. These measurements help us make decisions, plan activities, and communicate information. Their simplicity makes them indispensable in everyday situations. Vectors also play a big role in our lives even if we don't always notice them. When a pilot navigates an airplane, they consider both speed and direction, making velocity a vector. Engineers use vectors to design bridges and buildings, ensuring forces are balanced. Even athletes use vectors when calculating the best angle to throw a ball. Some of the most common scalar quantities include mass, temperature, energy, and time. These are measured in units like kilograms, degrees Celsius, joules, and seconds. Because they don't involve direction, they're easy to add, subtract, multiply, or divide in calculations. Common vector quantities include displacement, velocity, acceleration, and force. These are measured in units like meters, meters per second squared, and newtons. Because they have direction, you must use vector addition and other rules when working with them. Let's say you fill a tank with 10 liters of water, then add another 5 liters. The total amount is simply 15 liters. This is scalar addition in action. Just add the values and you're done. No need to worry about direction or orientation. Imagine you walk 5 meters east, then 5 meters north. To find your total displacement, you can't just add the numbers. Instead, you draw the two movements as arrows and use the Pythagorean theorem to find the resultant vector. This method ensures you account for both magnitude and direction. Suppose you buy 3 bags of rice, each weighing 2 kilograms. To find the total mass, you multiply 3 by 2, getting 6 kilograms. This is scalar multiplication, quick and easy with no direction involved. If you double the speed of a car moving north, the velocity vector also doubles in magnitude but still points north. This is an example of multiplying a vector by a scalar. The direction stays the same but the size changes. If you have a rope that's 12 meters long and you cut it into 4 equal pieces, each piece is 3 meters long. This is scalar division. Divide the total by the number of parts and you get the answer. If a cyclist halves their speed while heading west, the velocity vector's magnitude is reduced by half, but the direction remains west. This is vector division by a scalar, useful for adjusting speeds or forces in physics problems. When you push a box across the floor, the work done is calculated using the dot product of force and displacement. If you push in the same direction as the movement, the work is maximized. If you push at an angle, only the component in the direction of movement counts. This is a practical use of the scalar product. When you turn a wrench, the torque you apply is calculated using the cross product of force and the distance from the pivot point. The result is a vector perpendicular to both the force and the lever arm. This is essential for understanding rotational motion and mechanical advantage. In science, scalars are used to measure quantities like temperature, energy, and mass. These measurements are vital for experiments, calculations, and understanding natural phenomena. Their simplicity makes them a fundamental part of scientific research. Vectors are equally important in science, especially in fields like physics and engineering. They help describe motion, forces, and interactions between objects. Understanding vectors is crucial for solving complex problems and making accurate predictions. Engineers use scalar quantities to measure things like material strength, energy consumption, and time required for processes. These measurements help ensure safety, efficiency, and reliability in engineering projects. In engineering, vectors are used to analyze forces, design structures, and optimize systems. For example, when designing a bridge, engineers calculate the direction and magnitude of forces to ensure stability and safety. Vectors are essential tools in the engineering toolkit. In sports, scalar quantities like time, distance, and energy are used to measure performance. For example, a runner's time to complete a race or the total distance covered are scalars. These measurements help athletes track progress and set goals. Vector quantities are also important in sports. For example, the direction and speed of a soccer ball or the force applied when hitting a tennis ball are vectors. Coaches and athletes use this information to improve technique and strategy. To sum up, scalar quantities are simple, involving only magnitude and no direction. They're easy to measure, calculate, and use in everyday life. Whether you're measuring time, mass, or temperature, you're working with scalars. Vectors, on the other hand, require both magnitude and direction. They're essential for understanding motion, forces, and many scientific and engineering problems. Mastering vectors opens up a deeper understanding of the physical world. Conclusion: knowing the difference between scalar and vector quantities is fundamental for anyone studying science, engineering, or even sports. Scalars are all about how much, while vectors add the crucial element of which way. This distinction shapes how we measure, calculate, and understand the world around us. Thanks for joining us on this journey into the basics of scalars and vectors.